All right, so we still need to talk about how the kidney regulates blood flow too, because it is a major contributor to our blood pressure. So the first thing we're going to talk about is just sympathetic stimulation, which basically means if you are in fight or flight, you're running for your life, well, what happens then is that the afferent arteriole, which goes to the glomerulus, constricts. If it constricts, then you're not going to filter as much blood, so that means that you're not going to make as much urine, which that means that you're going to have more blood flow in the system, all right? You're going to have more volume, all right? So that's a big deal. The next thing is angiotensin II, and I want to go ahead and pull up the flow chart for angiotensin II because this is a great time to talk about it, and it's really important. So let's go ahead and bring that up. So if you look at this pathway, this is the angiotensin II pathway, and this is a great way to visualize how blood pressure and the kidneys are related. So if you look at that top part, it says blood pressure and blood to the kidneys decreases. Well, when that happens, those JG cells are stimulated. What do JG cells release? Right, renin. So they release renin, and renin's job is to change angiotensinogen to angiotensin 1. Well, what changes angiotensin 1 to angiotensin 2? Right, ACE. And actually this is where our ACE inhibitors work. So we can go ahead and write it right in. All right, ACE. So ACE changes angiotensin 1 to angiotensin 2. And look at what angiotensin 2 does. Angiotensin can either go and just cause vasoconstriction of the arterioles, and it is a potent vasoconstrictor. When you have a vasoconstriction of the artery, what happens? Right, you have an increase in blood pressure. Now let's go the other way. If angiotensin 2 goes to the adrenal cortex, what does it release? Right, aldosterone. And aldosterone's whole goal is to take water and salt out of the nephron on the kidney and put it back into the blood. So when this happens, your blood volume increases, again, increasing blood pressure and blood volume. So that's a pretty big picture. So let's go ahead and take it one step further, and let's just take a time and answer a question about this. Right, the correct answer is that an increase, not a decrease in ADH levels, which we briefly talked about, changes blood pressure. And we're going to talk about that in a little bit too when we talk about the posterior pituitary. So let's go ahead and talk about ADH now, since we brought it up in our question. So regulation of antidiuretic hormone and what it does in terms of blood pressure. Well, ADH goes to the collecting duct and says, hey, I need to take water out and put it into the body because either the body's dehydrated or it needs more blood pressure, okay? And so when that happens, you have less urine and more blood volume, more water in the system. Makes sense, okay? The other thing that ADH does is it convinces us that we're thirsty, and so we also drink more water. Remember when we talked about diabetes insipidus and pathology? That's the mechanism. So speaking of ADH and aldosterone, we're starting to talk a lot about renals. So it's a great time to talk about the urinary system and renal functioning. So let's go ahead and go to functions of the kidney. I think that functions of the kidney and kidney anatomy is very low yield. So I would just read through it and then let's move on. All right, what we have to talk about though is the nephron. And the nephron is the functional unit of the kidney. And what happens is you have a glomerulus, which feeds blood into something called a nephron. And we're going to draw this out and talk quite a bit about it. But when we talk about nephrons, there's actually two different types of nephrons. And I would know this because I think there's been a question about it in the past. So what we need to know is I would highlight cortical nephrons, okay? I want you to say that those are short loops of Henle, all right? So, and I remember it by cortical is kind of a short word versus juxtamedullary, which is a long word. And those are characterized by highlight long loops of Henle. And you're like, who cares? Well, the big picture here is that the longer the loop, the more urine it can produce, all right? So that's what they want you to know. So be aware, cortical, short loops of Henle, juxtamedullary, long loops. Also, there's a lot more cortical loops than juxtamedullary loops, okay? All right, so let's keep talking about this. How I'm gonna talk about it is I'm going to go ahead and we're gonna show you a picture of the nephron, and I'm going to add different pictures to it, in terms of the anatomy and what electrolytes are leaving and coming from here. So go ahead and I would just take time and draw it out with me, and then go back through your notes and we'll hit up those important parts. All right? So grab a piece of paper and let's draw this out. All right, so here we are going to start talking about the nephron. And this is also in the book if you don't have a piece of paper. But when we take a look at the nephron, we've talked before about the afferent and efferent arteriole. Notice how the afferent arteriole comes down and makes a capillary network called the glomerulus. Now, then it leaves the glomerulus and comes out as the efferent arteriole. Is this oxygenated or deoxygenated blood? Right, it's oxygenated blood. It is just a filter system so that the blood can become cleaner. Now, we talked about GFR in the past when we talked about pathology. So this is where glomerular filtration rate comes into play. So everything that goes into the nephron is being filtered. The more you can filter, the higher the glomerular filtration rate, and basically the cleaner the blood can be, getting rid of wastes, making more urine. So let's talk about the different parts of the nephron. So the first thing you have is the glomerulus, which goes into Bowman's capsule. And basically that takes all of the fluid, all of the amino acids, everything, and starts to act as a huge filter, all right? The first thing that everything goes through is the proximal convoluted tubule. Now, the proximal convoluted tubule is really where all the action happens. This is where almost all of the sodium and almost all of the potassium is absorbed here, all right? It is seriously the workhorse of the nephron. Also, the things that leave here are glucose and amino acids, bicarbonate, and water. So a ton of stuff. So let's go ahead and write that all out there. Now, look at bicarbonate. Can you think of something else that works here that we talked about within the respiratory system that was a big deal? Right, carbonic anhydrase also is here. Carbonic anhydrase works to also help either eliminate or absorb bicarbonate back into the system, all right? How about glucose? Should glucose continue in through the rest of the nephron? No, right? It is done. We should be spilling no glucose into our urine. So anything that escapes here should be taken from the PCT back into the bloodstream, all right? So let's keep on going. The next thing we have is the descending loop of Henle. Okay, the descending loop of Henle. There's not a lot of things that happen here except for water can leave. And one thing that's kind of crazy is that once water leaves here, it can no longer leave on its own. The only way it can leave on its own from here is if a medication or a hormone is acting upon it. Now we've reached the ascending loop of Henle. The ascending loop of Henle is highly permeable to salts. So it actively pumps salt and chloride from the loop into the interstitium, all right? And that's where it gets, again, picked up by the bloodstream to get circulated back around, all right? Remember, water does not leave here. The other thing, though, that can happen here is that there is a sodium chloride potassium co-transport that can move salts in and out with potassium. This is also where furosemide works. Furosemide is also called Lasix, and it's a great diuretic. And basically it works here in the thick ascending loop of Henle, and it inhibits sodium chloride potassium from being co-transported. When this happens, you get salts in the ascending loop of Henle, which then water follows it. And we know that water can't escape after that, so then it gets peed out, which is why it's a great diuretic. The other thing, though, that can happen is you get a state of hypokalemia because potassium also stays in the nephron and follows the water and gets urinated out of our system. All right? Okay, so continuing on. Next is our distal convoluted tubule. This part of the nephron is actually located in the cortex. So if you have any questions more about anatomy, I would be aware that it's in the cortex. So again, the DCT is impermeable to water unless it's acted on by a hormone. And in this case, this is where aldosterone works. So what happens is that aldosterone's main job is to take sodium and water and put it back into the bloodstream. So it takes salts and water and puts it back into the bloodstream at the expense of potassium. So if you have a medication that works here, which we do, it's called spironolactone, it actually makes this stop working. So one of the side effects then of spironolactone is also a diuretic. You get salts that remain in the nephron, which then water follows it and gets peed out, but potassium then stays in the bloodstream. And so a side effect of this is hyperkalemia, or too much potassium in the bloodstream. The last thing here that we're going to talk about is our collecting duct. Now, 8 to 10 distal convoluted tubules empty into each collecting duct. We're not going to draw that here, but I just wanted you to know that. So, as previously mentioned, water cannot leave here unless acted on by another hormone. And in this case, it's ADH. And we've already talked about ADH, but no, this is also a place where water can leave the nephron to go back into the body, as well as any sodium or chloride that is left in the system will also leave here. So we've talked a lot about things that are leaving this nephron. Well, where does it go? Well, there's this huge peritubular capillary network, which is an extension of the efferent arterioles that allows things to go back into the bloodstream, and that's called the vasa recta, okay? Basically, it's just like a big net surrounding the nephron where all of the sodiums and bicarbs and glucose can be reabsorbed back into the bloodstream. The vasa recta extends back into the cortex, and then it drains back into the venous system. So that is a lot of information, but basically it's the entire discussion about the nephron section by section. So if you want to go back through and just look at the different bullet points for each section along with following your drawing, I think that would be a great way to make sure that you have this whole idea of the nephron down. So just a couple things before we leave the renal system. One is you will see, if you go down past that picture of the nephron in the book, about a countercurrent exchange. And basically this paragraph here is just talking about the difference between a high and low gradient that the kidney uses to get concentrated urine. All right, if they ask any question there about what is the countercurrent exchange focused on or dependent to, I want you to know it's the ascending limb of Henle. All right, remember, lots of water goes out the descending limb of Henle, but whatever salts are in that ascending limb, water will follow to make sure that the gradient is more even. All right. Also, if you're asked any questions about what makes more concentrated urine, well, think about your own self and hemostasis, all right? So if you're dehydrated, you'll have a more concentrated urine, or different diseases can make you have more concentrated urine. But basically, dehydration or any state where there's a decrease in plasma volume, all right? There's also a box down there about a kidney dialysis machine. And a kidney dialysis machine is somewhat like the countercurrent exchange, but it's called a countercurrent multiplier. And I would highlight that and know that. And basically, it makes this artificial way that there's this countercurrent exchange so that a kidney that cannot work goes through an artificial machine that can make that exchange happen in terms of getting the fluid off the body and maintaining that homeostasis with the different electrolytes. It's a very long process. I would just know though that box and that it's considered a countercurrent multiplier. All right? Okay, so if we keep talking about renal, we also need to just re-go through this idea that the renal system is also what helps us keep our pH in balance. And we already talked about this when we talked about the respiratory tract, right? But basically, when we talk about how the kidneys regulate the pH, it's all about what is happening, where do you think, in the nephron? Right, the proximal convoluted tubule, because what is here? Right, bicarb and hydrogen ions can leave the proximal convoluted tubule here. And the determination of that depends on how much acid or bicarb leaves our system or how much stays in the bloodstream. So, for example, if we are in a state of an acidic environment, so we have an acidotic bloodstream, well, then what's going to happen is our body is going to need to take more bicarb from the PCT and use it to its advantage to help increase the pH or make it more alkalytic, right? Okay. Also down here we're talking about ammonia, and we just need to make sure we're aware of what that is. Ammonia is NH3. Epithelial cells in the PCT are responsible for producing ammonia. And this is done through the catabolism of glutamamine, and I would be aware of that, so highlight that, okay? Awesome. All right, so good. So we can start moving on from this. There's a little bit about this in biochemistry that I think Kyle will be talking about. Otherwise, let's go ahead and start talking about the endocrine system. So we are at endocrine, everybody, and there are a lot of questions about endocrine. So we are just gonna dive in and enjoy it and go through all these different hormones, their diseases, and all these important facts about our endocrine system. So let's start with the hypothalamic hormones, all right? Now there are either releasing hormones or inhibiting hormones, but you know it's coming from the hypothalamus because it literally has that in the name. And I put a chart there just so that you could see the hormone and its activity. I would be aware of that. But basically, you have your thyroid releasing hormone, your corticotropic releasing hormone, your gonadotropic releasing hormone, growth hormone releasing hormone, somatostatin, which is inhibitory, and that inhibits the release of growth hormone, and your prolactin inhibitory factor, again, inhibiting prolactin release. So I would just be aware of those, all right? So we'll talk about those in just a second. But first, I want to go ahead and go to the synthesis of peptide and protein hormones. And you can see in the book that there is a flow chart of genes, and it goes all the way down to the hormone, okay? Well, there's 5 things that I want to go ahead and write out, and I'm actually going to go ahead and put them on the screen for you because I think they're really important and they're not in the text, all right? So let's go ahead and do that. So a couple things I want you guys to know about protein and peptide hormones is that 1, they're stored in secretory granules. 2, they're synthesized to a precursor form. 3, they act by using a second messenger to reach the target tissue, and that is usually cyclic AMP. Okay? And then 4, they're transported unbound in plasma. So the reason why I want you guys to make sure that you know all of those about the peptide and protein hormones is that there have been some questions in the test about it in the past. So let's go ahead and just kind of take a break mentally and go ahead and look at one of those questions. Right, they bind to intracellular receptors. Remember, these actually act by using a second messenger to target the tissue that they're trying to get to, all right? Okay, good. All right, let's also continue then, and I want to look at the that next flow chart on the page that you're already on, and that's about your cholesterol hormones. Now remember, anything derived from cholesterol, you can go down and do sugar, salt, or sex, all right? Sugar, salt, and sex, because cholesterol-derived hormones are your salt, so your aldosterone, your sugar, think of cortisol, and your sex, which are your estrogens and your testosterone. So if there's any question about the precursor for all of those, it's cholesterol, all right? Okay, good. Now let's go ahead and let's start thinking about the pituitary hormones, all right? And remember, we started talking about which ones are anterior and posterior. So we're gonna start again in our anterior pituitary hormones, and those pituitary hormones are ACTH, TSH, growth hormone, LH, FSH, and prolactin, all right? We're gonna slowly go ahead and go through those. The one we're gonna start first is ACTH. Now, for each one of these hormones, I put a picture so that you guys could see where it's coming from and where it's going, okay? So for example, those pituitary tropic hormones, you see they come from the hypothalamus, and they either go to the adrenal cortex or the thyroid gland, okay? And those 2 pictures are close together. I would know that fact, okay? Hypothalamus, they go to the adrenal cortex and go to the thyroid gland, for example, okay? But if we look there, I also then just wrote in paragraph form for you guys the hormone and then to where it's going, all right? So let's take a look at ACTH first. And I want you guys to know that it goes from the hypothalamus to the anterior pituitary to the adrenals, and it's the adrenal cortex. And this is gonna be what helps release glucocorticoids from the adrenal gland. So the next one is TSH, and we already talked about TSH in pathology if you watched the video. So TSH goes from the pituitary gland and it stimulates the secretion of the thyroid hormones, okay? So T4 and T3. Now in pathology, make sure you go and you watch that video because it in depth talks about the different diseases and the hormone control. But I also talked about it here again, so let's revisit it. So remember, when TSH comes, it's actually stimulated by the hypothalamus releasing, thyroid releasing hormone, all right? And that's going to stimulate the anterior pituitary to then release TSH. TSH is then, we know, it goes to the thyroid gland and helps release T3 and T4, all right? So we talked about some diseases, but we haven't really mentioned iodine. So let's just go ahead and ask a question about iodine, and then we'll start a conversation, okay? So take a look at this question. Right, the answer is thyroglobulin. Thyroglobulin is a protein in the thyroid which the thyroid hormones are synthesized in. Good, so we know then that if you have an increase in thyroglobulin, then you have an increase in your T3 and T4, okay? So let's keep going then. So we know a healthy thyroid gland has enough T3 and T4 for lots of different things. Our thyroid gland, and I would highlight these in that second bullet point because any of it could be picked on for your test. But thyroid controls growth and development, temperature regulation, and then daily energy requirements, which makes sense, right? When we talked about the patient who had decreased thyroid gland and they were slow and they gained weight and they were cold, all right? All those things are regulated by the thyroid. The other thing is I put in that box hypothyroidism again, and just some of the clinical states. Highlight in there mixed edema. I don't think I've mentioned that yet, but you also need to know that mixed edema is in here as well, and that has been picked on before on tests. So when you think mixed edema, think hypothyroidism, all right? Also then, if they ask what other things can stimulate T4, make sure you're thinking about the things that it controls. So for example, somebody who's been out in the cold for a really long time, their thyroid is actually gonna kick in and release more T4, because again, it's part of temperature control. All right, that should make sense, good. Okay, so let's move on from there. Now we're going to talk about growth hormone, okay? We're still in the anterior pituitaries. Growth hormone is responsible, obviously, for growing. And if we have growth hormone deficits, then that's going to cause dwarfism and other short stature issues. Also, growth hormone deficiency can be caused by some different things. If you have hypothalamus dysfunction, if you have pituitary tumor, that can cause it. So anything upstream, if you have a decrease in the hormone, it's going to cause a decrease with your growth hormone. Also, just abnormal synthesis, or if you have some sort of receptor disorder, that can also cause a decrease in growth hormone. So let's talk about growth hormone excess, all right? What happens? Well, it's going to go one of two ways. If you have growth hormone excess before you reach puberty, you're going to be giganticism, okay? If you have an excess of growth hormone after puberty, that's when you get acromegaly, all right? In the past, they have wanted to know some questions about growth hormones, so let's just go ahead and ask one, all right? Take a look at this question. Right, somatotropin. Another name for this, growth hormone. All right, well, let's continue on. So next we have FSH, which is follicle stimulating hormone, and then LH, and I would definitely know these as well. So FSH, what I would look at is the chart on the next page where it talks about where FSH is going. So I want you to know that it goes to the ovaries and the testes. That's a good test question, because when we think about FSH, we only think about female endocrinology, but it goes to both, okay? So it stimulates the development of follicles in the ovaries and causes spermatogenesis in the testes. I would be aware from that. Also, LH is again in both men and women. We'll talk about it more in women, but I want you to know that it also stimulates secretion of sex hormones as well as ovulation. So female sex hormones include estrogen and progesterone. Male sex hormones includes testosterone. And if you look at the chart, you can see how in the female and the male, they're both there, how FSH and LH work to stimulate those hormones. So I would take a second and just look at those, all right? Otherwise, we're going to go ahead and move on. They ask actually quite a bit of questions in the past just about a menstrual cycle and how these hormones come into play. So I'm going to go ahead and let's put up a drawing of this and follow along. So let's take a look at just the physiology of a woman's menstrual cycle. So the first day is day 1 of menstruation. The last day we'll say is day 28 because on average it's a 28-day cycle. So that would be the day before a female starts menstruating again. Now, if we cut this into half, about day 14, on day 14 there's something called an LH surge. And guess what? That's caused by luteinizing hormone, or LH. All right? LH surge releases an egg. And we want to know exactly what that egg follicle is called, and it's released from a Graafian follicle, okay? The Graafian follicle then releases an egg into the fallopian tubes and through the uterus. At this time, it can be fertilized and become a baby, or if no fertilization takes place, it ends up not connecting to the uterus, but instead hormones decrease and the cycle starts over again. The first half of this phase before day 14 is called the follicular phase. That starts on day 1 of the cycle. The second stage is called the luteal phase, and that starts at the beginning of ovulation and goes until the next bleeding cycle. During the follicular phase, FSH is high, and that's what stimulates the follicular development, maturation of the ovum, and then secretion of estrogen. At day 14, after the LH surge, progesterone increases. When progesterone increases, that inhibits further uterine endometrial growth. That way, if pregnancy occurs, it can be properly planted into the endometrium. So that requires another hormone, which is called chorionic gonadotropin. That's secreted by an embryo. If we have the presence of chorionic gonadotropin, then pregnancy has occurred and menstruation will not take place again. If there is no embryo, then progesterone levels decrease, as does estrogen, and the cycle starts over. So that is a lot. But I think that there will be test questions taken from that. So if you were following along, you'll realize that we kind of skipped over estrogens and progesterone. So just a couple of things to take away from that, okay? Highlight right under estrogens and progestins that estrogens basically promote the growth of the endometrium. All right, they promote the growth of endometrium. If you have too much estrogens over time without menstruation, that can cause endometrial cancer. And I would be aware of that because I believe that's been on the test in the past, okay? The other thing is progestins. Those are hormones that promote gestation. So when you are pregnant, your progesterone stays really high throughout the course, all right? Okay, so let's continue and we're gonna keep going, and the next one we're gonna talk about is prolactin. So what I want you to know about prolactin is that, one, it's inhibited by PIF, prolactin inhibitory factor. Do you guys remember where that is released? Right, the hypothalamus. Make sure that you can work these hormones back, all right? Also, what happens with prolactin? What does it promote? Prolactin promotes milk production, all right? That's what you need to know for that. All right, let's keep going. You guys are doing great. And guess what? We're on now to the posterior hormones. And there's only two. Awesome. So the first one is ADH. And we've talked a ton about ADH. So I think we can just skip over it here. There is just a reminder about what it does. So you can take a look at that. And then the next one is oxytocin. So oxytocin actually kind of works in conjunction with prolactin. So remember, prolactin promoted milk production, and oxytocin is going to allow for milk ejection. All right? Okay, let's take time out and let's look at another question. So take a look at this. Right, diabetes insipidus, because we would have a decrease in ADH. So those are all the hormones that we think about coming from the hypothalamus, pituitary. So now we're going to talk about endocrinology of calcium and phosphate hemostasis. People, there have been a lot of questions about this in the past. So this is one of those things that you need to know what they are and what they do. All right? Good stuff. So the first thing we're going to talk about, I want you to go down to bone formation, okay? So we're talking about bone formation, a couple key things here. You need to know what it is stimulated by and what it is inhibited by, okay? So we're talking about bones. It's stimulated, and you can just read through these: growth hormone, insulin, estrogen, androgens, vitamin D, and calcitonin, okay? Highlight calcitonin for sure. That's a big one because we're gonna start talking about parathyroid hormone as well, okay? So bone reabsorption. So when you think about bone reabsorption, we need to figure out what that is caused by. Bone reabsorption is stimulated by parathyroid hormone, vitamin D, and cortisol. Makes sense, okay? It's inhibited by highlight calcitonin, all right? Also estrogens. One thing that's interesting about estrogens is that estrogen plays a big role in bone health. And after a woman goes through menopause and their estrogen drops, that's when they lose the most amount of bone mass that they will throughout the rest of their years. In terms of a huge drop off in estrogen also causes our bones to become fairly weak. So that's when we start needing to think about DEXA scans and definitely calcium replacement, okay? But getting back to bone formation reabsorption, you guys can read through active osteoblasts in class. That's going to be hit in another chapter as well. But I want to go to where we start talking about the parathyroid gland, okay? So we talked about this in pathology as well. But the parathyroid gland, it is responsible for monitoring and deciding how much calcium we need in the bloodstream, okay? So the parathyroid gland has two types of cells, all right? It has chief cells and it has oxyphil cells, okay? Parathyroid hormone, highlight this, it is synthesized in the chief cells, okay? Blood calcium levels control parathyroid hormone. So if you have a decrease in blood calcium levels, guess what's gonna happen? You're going to have an increase in PTH, all right? So a decrease in blood calcium means that you're going to have an increase in PTH because you need more calcium in the bloodstream. And then vice versa, right? So if you have too much calcium in the bloodstream, there's going to be a decreased amount of PTH. So PTH then enhances reabsorption of calcium in the PCT of the kidneys. I would look at that second bullet point and highlight that. Also, go down to the very bottom bullet point. This is important too when you're underneath PTH, is that it inhibits reabsorption of phosphate by the kidneys. Okay, just be aware of those things as well. All right, so let's go ahead and take a look at a question about what or how they could ask this. Okay, so look at this question. So serum calcium is decreased because you don't have enough parathyroid hormone, and serum phosphate is increased. And if you think about it, that's because of that bullet point underneath the parathyroid hormone where it says it inhibits the reabsorption of phosphate by the kidneys. If you don't have a lot of parathyroid hormone, there will be no inhibition of reabsorption, so you will have more increased phosphate into the bloodstream. So calcitonin is synthesized by the parafollicular cells in the thyroid gland, okay? So calcitonin you need to think about as the antagonist of parathyroid hormone, right? When one is up, one is down. When one is up, the other's down, all right? They're constantly antagonizing each other, all right? So the thing that you need to know about this is it is going to inhibit osteoclast activity. Highlight that, it's in the paragraph, right? So if you have an increase in calcitonin, where's the calcium going to go? It is going to go to the bones. Good. So if you have a decrease in calcitonin, where is your calcium going to go? Right, it can't go into the bones, so you're going to have an elevated serum creatinine. Okay, good. So what does it look like when you have a patient with too much calcitonin? One thing I want you to remember here, too much calcitonin, right, it's all in the bones. That means my serum calcium is low. So I want you to think of muscle spasms, right? Tetany, because calcium is really important for muscles. You can also get a lot of heart palpitations and contraction issues, because again, that's a muscle. Also, you can have mood swings and different psychiatric issues because of that. All right, good, awesome. Okay, let's move on to the pancreas. So we've talked about the pancreas just a little bit in pathology when we talked about obviously diabetes, right? But let's talk about the endocrine functions of the pancreas. Now the pancreas has 3 cells that we need to think about. One is alpha, 2 beta, and they skipped C and now we have delta, all right? So alpha, beta, delta. So the alpha cells, they secrete glucagon, all right? You need to know that. Alpha cells secrete glucagon. Beta cells secrete what? Right, insulin, okay? When we think about alpha cells and glucagon and insulin, those also are antagonistic of each other. I would know that glucagon, what it does is after a state of fall in blood glucose, so after you've been fasting, this is when glucagon kicks in, and it's going to stimulate the liver to convert glycogen to glucose, okay? And that's called glycogenolysis, okay? So we have glucagon, which causes glycogenolysis in the liver. On the other hand, insulin is released after you eat a lot, okay? When there's a state of high glucose in the body, and that's going to promote the glucose to go into the cells to be used for energy, okay? So when we have a rise in insulin, our glucagon is going to fall, which obviously makes sense. So look at that box. It says basically actions of insulin and glucagon are antagonistic. After a meal, insulin is elevated. After fasting, glucagon is activated. So I would be aware of that, okay? Those delta cells, moving on to those secrete somatostatin. Now we've heard about somatostatin somewhere else because it's also released from where? The hypothalamus, good. So somatostatin is an inhibitory hormone against what? Growth factor, good. So it inhibits growth hormone, it inhibits the thyroid stimulating hormone, and also gastrointestinal hormones, all right? The other thing is that somatostatin is not only from the pancreas, the hypothalamus, but also the stomach and the intestine. So we can see these in various places, so I would know about that. We've also talked about the problems when you have insulin disorders, which of course would be diabetes, right? So again, that's there. The other thing that is here that I would just review is I have type 1 diabetes, type 2 diabetes, as well as kind of the physiology behind those. Make sure that you review those again as well, all right? The only other thing too that I would add is when we're talking about things that insulin does, one thing I would add is that it also increases phosphofructokinase, okay? Make sure that you add that in there as well, just in case it's one that they pick on for your exam. You can go ahead and review all of that, but mostly focus on that in pathology, all right? So, since we're reviewing here, let's go ahead and add a question, all right? So take a look at this. E, good. If you have hypoglycemia, you actually will have hypoventilation. Awesome. All right, let's go ahead and move on to the adrenal gland. Now remember, what does the adrenal gland produce? Sugar, salt, sex, right? Well, we're going to talk about our glucocorticoids and our mineralocorticoids here, okay? We've already talked about estrogens, or I should say testosterone, estrogens, LH. We've talked about all of those, okay? And remember, FSH, they go to ovaries and testes, as well as LH goes to ovaries and testes too, okay? All right, so our glucocorticoids, cortisol and cortisone, mineralocorticoids, that's aldosterone or deoxycorticosterone. I think the big thing to remember with this is just one, where do they come from? The first area here is the adrenal cortex. So make sure that you know that the adrenal cortex has the glucocorticoids and the mineralocorticoids. I also just put there all the things and bullet points that glucocorticoids do. So remember, this is cortisol. So you just think steroids, okay? So anything a steroid can do, that's what cortisol, your glucocorticoids can do, okay? So they can have too much blood glucose, right? Increase your glucose in your blood. Promotes insulin resistance. Those are two big ones. If you go way down, chronic use can lead to immunosuppression. It's hard on your bones, all those good things. Technically bad things. So you can go ahead and just look at all that list. The mineralocorticoids, again, we've talked about it, but aldosterone. And remember, aldosterone does what? Yes, it increases blood pressure by taking salts and water out of the nephron and putting it back into the bloodstream. All right, good. All right, let's continue. The next part of the adrenal gland is the adrenal medulla, all right? And this is your catecholamine spot. And I know that Kyle's going to talk a lot about epinephrine and norepinephrine, but basically this is where they are released. So these are your fight and flight. So when we talk about actions of catecholamines on the body, it's all your fight and flight. So you can read through those. Again, some big ones is you're going to have increased blood pressure, increased contractility, increased stimulation of glucagon release and gluconeogenesis. Just go through that list and make sure that you're aware of all the different things that epinephrine and norepinephrine can do.